I'm Anil Kumar. Welcome to my series on advanced functions. I hope you have enjoyed this journey of learning about different kinds of functions. Now we are almost at the end. It is time to test our knowledge. In this particular video, I'm talking about three real life situations. We have actually modeled them for you. You need to analyze the situation and answer related questions. Here is the very first one. We're talking about population of owl and mice. Trigonometric equations are given here to model the situation. And then you have four relative questions. You can always pause the video, answer this question, and then move on. The other two questions are kind of similar, but with different functions, right? The second one here is based on rational functions, and we are talking about the most important device now, cell phones. So here we need to minimize the shipping and storage cost of cell phone where a rational function gives the cost. Four related questions again are there for you to discuss. The last question which we have taken up is again based right from the nature. I love nature, and after this we'll just see the beautiful nature of Canada, light snow, lots of animals and birds, and then we'll look into how to solve and answer these questions, right? So here we are releasing frogs in the environment and trying to figure out what will happen to their population over a period of time. I hope you find this video interesting and useful. Now let's take a small break and watch nature, and then we'll begin with the solution of the very first question, talking about owls and mice. Snowfall. I hope you enjoyed the video. Let's get back to our solution. The question here is, the population size capital P of owls, predators, in a certain region can be modeled by the function P of t equals to 1000 plus 100 sine pi t over 12, where t represents time in months. Population size of lowercase p for mice, the prey, in the same region is given by P of t equals to 20,000 plus 4,000 cos pi t by 12. The four parts of this question are: at what time is the population of mice at the minimum? How is population of owl related with that of mice? C. What might be the meaning of the function y equals to capital Pt minus lowercase pt? D. What is the population of mice when population of owl is 975? You can always pause the video, answer this question, and then look into my suggestions. Now let's try to analyze. We're looking for what is the time, at what time is the population of mice at the minimum, right? So let's look into the population of the mice, which is given by this equation here, right? So I'll kind of sketch this right here. So I prefer to make light, approximate diagrams, which gives you the situation, the gist of the situation, and this small space will help us understand the whole explanation, right? So we are saying population of mice, which is given here. So P of t, so lowercase p with time. So it is a cosine function which starts with the maximum, correct? The axis is 20,000. So what I can do here is kind of draw something like this. Right, so this is one cycle. Perfect. Now in this one cycle, what we can notice here is that the axis is 20,000, right? So this axis is 20,000. 4,000 more, that is the amplitude, becomes 24,000, right? And 4,000 less will be the minimum, which is 16,000. So we get the numbers. Now as far as the time period is concerned, we have pi t by 12. So let's find the time period. Time period t should be equal to 2 pi divided by what we get here, pi by 12. So let me write here pi divided by 12, correct? So that goes in the numerator, pi and pi cancel, so we get 24. And that is in months, right? So we get 24 months. That is along the time. Perfect. So that is how you could see the population of mice. Now the question is, at what time is the population of mice at the minimum? Clearly, it is half the cycle, right? So that is the time when it hits the minimum, right? So this is after 12 months. So we get the first answer, which is 12 months. T is time in months, right? So T represents time in months. So I hope that is absolutely clear, straightforward, right? So that's the huge advantage of modeling. So once you have an equation right in front of you, it's kind of much simpler to answer the questions, right? Now let's look into the second equation, which is how is the population of owl related with that of mice? Okay, so we're given this population of owl. We'll actually see a small sketch and then answer the equation, correct? So I'll try to make a similar type of scale. Okay, now population of owl. Okay, let's choose a color. That's fine. So this is owl population, capital P. It is a sine function, right? So sine function is going to start from the axis itself. So, and it goes, right, so that is how it is going to be. So let me just sketch this sine function. Okay, so approximately, that's fine. So we get a sine function here. Now in this sine function, we start with the axis which is given to us as 1000. So this number here is 1000 and 100 more, so 1100. 100 less gives us the minimum, 900. Perfect. Now it says, how is population of owl related with that of mice? Well, as you can see, the population of owl increases. As the population of owl increases, the mice population decreases. Do you see that part? So the mice population hits the bare minimum after 12 months. However, the owl population takes another 6 months to get to the minimum, right? So this is at 16 months. So this is at 16, that is 24, this is 12. Perfect. Well, it gets its maximum in the first 6 months. So from here, what we can see is that the population of owl follows that mice. So that is easy and understandable term to use. So we say the population of owl follows mice. Does it make sense? It kind of lags behind, but it's just catching up, right? So as the mice population falls, right, this also starts falling, correct? And it actually reaches its maximum after 6 months. So there is a 6-month gap phase. You can say that. Perfect. However, once the owl population becomes minimum, then the mice reproduce faster and they kind of increases. So the duration when the owl population is kind of decreasing, right? So you find that the mice population increases and then owl population follows. So basically, the owl population reaches its maximum 6 months after the mice's maximum, and it hits its bottom when the mice population has already done so 6 months back because of lesser food available. Perfect. So that makes huge sense. Now let's talk about part C, which is what might be the meaning of the function capital P of t minus P of t. So this is your capital P of t, right? The owl population. Now what do you understand by this particular relation? Now, this is a key part which many of my students could not understand. So I'd like you to comment on this. Now if you just check the numbers and if you do, let's say 1000 minus 20,000, you get negative numbers, right? Remember, these numbers cannot be negative. Perfect. So one should remember here that both capital P of t is greater than or equal to 0 and the lowercase p of t is also greater than or equal to 0. Perfect. So what does this mean, capital P of t minus lowercase p of t? So we have to look at into a broader sense of mind. We're talking about a cycle, right, where things are dependent on one another. So what do you see here? You see here a very healthy environment, ecosystem, I should say. So the populations of both mice and owl recovers and the cycle is maintained. Perfect. So minus P of t means what for us? Correct? So let's look into this. Minus P of t. So if we minus P of t, that means we are removing the mice. That means remove mice. If the mice are removed, owl will not have any food there. Perfect. Based on this information provided. So what do you notice here? They're within 6 months because they're just following the mice. Owl will also vanish. So as this becomes lower, right, approaches 0, I should say, then the capital P of t, which is the owl, right, will also diminish, right? So decrease, approach to 0, correct? So the whole system will collapse. So that is what the real answer is. So removal of P of t means collapse ecosystem. Perfect. So that is the broader meaning of the equation y equals to capital P of t minus P of t. If I put it the other way, that is to say P of t minus capital P of t, that is to, in that situation, what is going to happen? Well, if there are no owls, the mice population will explode. They will actually eat their own environment and ultimately they will also die. Perfect. So for the ecosystem to be healthy, it is important that a proper balance is maintained so that these equations and the given situation gives you that proper balance. Perfect. So I hope that part is absolutely clear. Now let us answer part D. What is the population of mice when population of owl is 975? So let's find the time and then work it out. So we'll do it on a fresh page. Now let's do some algebra with these equations. The population size P of the owl is given by the equation P of t equals to 1000 plus 100 sine pi t over 12, and population size lowercase p of mice is 20,000 plus 4,000 cos pi t over 12. The question here, which is part D for us, is what is the population of mice when population of owl is 975, right? So population of owl is given by P of t. So what we are given here is P of t is equal to 975, right? And the equation is 1000 plus 100 sine pi t by 12. Now first thing, when you need to solve this equation, since there is pi involved, we have to change our scale to radians. So first thing is change your mode to radians. In my calculator, it is option 4. Now once you do that, then you do your calculations. Otherwise, you might just get a wrong answer. So let's rearrange. So we get 975 minus 1000 equal to 100 sine of pi t by 12. Now good part is that cos of pi t by 12, we need to find the whole thing. You need not really worry much about t, correct? So we get here negative 25 over 100 equals to sine of pi t over 12. Correct? So from here, now this is negative. It really means what? Let's review as we move forward. That really means that, let me show it here. Sine is negative. Sine is negative, we know the rule. That means we are either in quadrant 3 or in quadrant 4. So we'll take up this position. Is it okay? So that is when this sign is going to be negative, right? So let's find the angle beta here. Is it okay? So I'm replacing this with 0.25 equals to sine of related acute angle beta, right? So beta is equal to sine inverse of 0.25. So let's use calculator to find this. It's already in radians, right? So sine inverse of 0.25 is equal to, we get a value which is equal to 0.25268. Now that is the value of beta. Now what is the angle? That is to say, what is pi t by 12? So this will be all this. Do you see this? That means pi plus this. So we get pi t by 12 as equal to pi plus 0.25268. Does it make sense to you, right? So we'll just add pi to it, right? So we'll add pi to it, and what do we get? We get this as equal to 3.394, let me write this as 43, right? So I'm rounding this. So that is the value of pi t by 12. You get the idea, correct? Now, we have to use this value of pi t by 12 to find the mice population. Does it make sense? So what we found here is that the pi t by 12 is equal to 3.3943, right? This is in a radian, basically is a ratio. Perfect. Okay. Now we'll use the second equation, which is lowercase p of t, and we'll substitute this value. Perfect. So we get p of t is, we didn't really find time. Perfect. We just found the whole thing, which is pi t by 12 equals to. So we'll replace the whole thing. Is equals to 20,000 plus 4,000 times cos of all this, which is 3.3943. Correct? So let's calculate. So we already have the number there. So we'll say cos of the answer is equal to, we'll multiply this by 4,000, right? And then we are going to add 20,000 to this to get our answer. So I hope you find these calculations simple enough. 16,127. That is what you get. Always the population has to be a whole number, right? So we get 16,127 as our answer, right? So that is how you are going to provide the solution. So those many mice. So our answer is population of mice will be 16,127 if the same model is followed, correct? It makes sense, as you can see from here, that if the population of owl, so if you see from here, if the population of owl falls, that is to say, below 1,000, right? So somewhere here, below 1,000, right? So in that case, the mice population is recovering, right? So it is kind of here. Does it make sense to you? So this value, we have taken the very first value. Well, it could have the other answer also. So some of you, what you can do is also find 975 on the other side. So at that time, by that time, the population of mice has almost recovered, right? So that could be the other solution. Perfect. So what I'm trying to say here is this is one solution. So we'll say case 1. And let's do case 2. And in that case, I'm going to add, rather take away this number 0.25268 from 2 pi. So let's do that part, right? So it could be taken as minus of 0.25, right? So we could also see that. So we have now shift pi times 2 minus 0.25268 equals 2. So that gives you the value is 6.030. So that gives you, so pi t by 12 could also be 6.0305. Correct? So you could use this value and find the second answer. So let's use this value, or which is also correct. So P of t is, that is on the recovery path, right, is 20,000 plus 4,000 cos of this number 6.0305. Let's figure out how much is this answer. So we'll do cos of 6.0305, multiply this by 4,000 and then add to 20,000. So what we get here is equal to 23,872, right? So it is to 9.9, it could be rounded to 3. So we get a much higher population. Perfect. So that means it has almost recovered, right? So 24,000 is the maximum. Perfect. So this is on the recovery path. So you could also find the other solution, which is on this path. So at that time, pi t by 12 is this angle. Correct? So for the owls at this level, mice population on the recovery path could have been 16,000, and when they have almost recovered, close to 24,000. So these are the two solutions for the given question. So I hope you understand the whole concept, and I hope you appreciate it. So let's take a small break, watch some more nature, and then get to our next two questions. I hope you really learn from this experience at the end of your course. Here is an application question for you. The cost C in dollars for shipping and storing n cell phones can be modeled by the function C of n equals to n plus 100 over n. Graph the function and explain its shape. Write domain for the function. Determine minimum and maximum number of cell phones that can be ordered at any time to keep cost below $55. Assume zero inventories on hand. Part D is, what is the optimum order size that will minimize storage cost? You can always pause the video, answer the question, and then look into my suggestions. So let's begin by graphing C of n equals to n plus 100 over n. Now here, n has to be greater than 0. Since it is in the denominator, it cannot be 0. So n is greater than 0. We are talking about cell phones, and therefore the numbers are whole numbers, right? So we are non-negative integer values. So as far as the domain is concerned, let me write down domain of this function. So we can say domain is n belongs to natural numbers, right? And we'll say n is greater than 0. Okay. Now let's talk about the graph itself. The graph of this function will have an oblique asymptote, which is as n approaches very large value, 100 over n will approach 0. So y equals to n or cost equals to n will be the oblique asymptote, right? So I'll sketch a small graph here. We'll answer the question in the rest of the page. If n equals to 1, then the value is 1 plus 100, which is 101, right? So the value starts with 101. Now, as the value of n increases, if n becomes 2, then it becomes 2 plus 50, which is 52, right? So what you notice here is that the value of the function is higher first, then it decreases, and then it is going to increase. And let us assume that at n equals to 1, we have this value, which is 101. We can make a table of values to get rest on this graph, but that is the shape of the graph. Oblique asymptote will be C of n equals to n, right? So we can say as n approaches infinitely large value, C of n will approach n, and that too from above, since this is a positive value. Correct? So that is all about the graph. Let me label this as n in numbers and the cost C in dollars. Determine minimum and the maximum number of cell phones that can be ordered at any time, any one time, to keep the cost below $55. So well, the minimum number is 1. Now we need to keep the cost below $55. That is to say, the value here, n plus 100 over n, should be less than 55. We can say less than equal to $55, right? You can solve this as an equation. So we get n squared plus 100 equals to 55n. Bringing them all together, n squared minus 55n plus 100. Let's say equals to 0. Let's solve this. So let's use the quadratic formula. So n equals to minus of b, which is 55, plus minus square root of 55 square minus 4ac. So when you do minus 4ac, it becomes minus 400 over 2. So let's calculate this value. So we have 55. So we'll take positive value, positive square root 55 square minus 400 equals to, and we're going to divide this by 2, and the decimal value here is equal to 53.1, right? So the maximum value of n can be 53. So that means for this cost, the value of n will be greater than equal to 1 and less than equal to 53. When we are assuming the maximum cost as equal to $55. Part D is, what is the optimum order size that will minimize the storage cost? Now, to minimize the storage cost, we have to see the rate of change, and the critical number will be when this rate of change is 0. So let's find the critical number by taking the derivative of this function, which will be 1 minus 100 over n square. And we need to equate this to 0 to find the critical number. Now, those of you who haven't done calculus at this stage may actually make a table of values, and for different values of n, they can find the cost, right? So for them, I'll suggest make a table of values. So write down different values of n and then calculate the cost using the formula, taking n as 1, 2, 3, 4, 5, and so on, correct? Some values, they will give you a good idea because we are looking for this particular point here. Now from this calculation, equating it to 0, we can solve this as n square equals to 100. So that gives you, this is n square equals to 100, or that gives you the solution as n equals to 10. So at n equals to 10, we are going to get the minimum cost. So when you work out for n equals to 10, you can write down 10 here and you say the value will be 10 plus 100 divided by 10, which is also 10. So we get the cost as $20. So we'll find C of 10, the function C of 10 is equals to 10 plus 100 over 10, which is 10 plus 10 or $20, correct? So that is the value in dollars for the cost, and this is the minimum value, $20. So that is how you could actually do. So those of you who haven't done calculus so far, they can calculate the values, and once you calculate the values, you will find that the minimum cost is $20 when the order of 10 numbers is placed. Perfect. So I hope that gives you a fairly good idea about how to solve such questions. The question here is, let P represent the size of the frog population in a marsh at time t in years. At t equals to 0, a species of frog is released into a marsh. When t equals to 5, biologists estimate that there are 2,000 frogs in the marsh. 2 years later, the biologists estimate there are 3,200 frogs. Find a formula for P equals to G of t. How many years will it take for the population to grow to 10,000 frogs? Does this seem reasonable? So that's the question for you. You can always pause the video and answer the question. Now, let us first get the model. Now we'll assume exponential model in this case. Normally in such situation, that is the best model to pick. Now P represents the size of frog population at any time t. So let's call P of t as the population of frog at any time t, where t is in years. And we'll define a variable P0 as the initial number of frogs introduced. And let R be the rate of growth and t the time. Now we know that after 2 years, after 5 years, when t equals to 5, estimated population was 2000 frogs. So let's write this. So we got 2000 here. We don't know the initial population. We don't know the rate of growth, but we know that after 5 years, this was the situation. So that is our equation number 1. Two years later, that means after 7 years, the population grew to 3200. We are assuming the same rate of growth, right? So now if I divide one equation by the other, then we can find the value of R. So 2 divided by equation 1, right? So we get 3200 divided by 2000 equals to P and P cancel. R to the power of 7 minus 5, which is, well, let's write R to the power of 7 over R to the power of 5, which is R square, right? So from here, we get the value of R as, now this is when you cancel, so it is 1.6, right? So square root of 1.6 is equal to R. Square root of 1.6 is equal to, in decimals, 1.265, let us say, right? Okay, so that becomes the rate of growth, 1.265. Once we know the rate of growth, we can find the initial population introduced using any one of our equations, right? So let's use the first equation and find P0. So what we get here is 2000 equals to initial population. R value is 1.265 to the power of 5, correct? So from here we get 2000 divided by 1.265 to the power of 5 as the initial population. So it is 2000 divided by 1.265 to the power of 5, which is equal to 617. Right. So it is always a round number. So we'll take 617 as our initial population, and that gives us the formula, which is P of t at any time the frog population, and t is year since it was introduced, it is equal to 617. R is 1.265 to the power of t. So we've done part 1. Now B, how many years will it take for the population to grow to 10,000 frogs? Does this seem reasonable? Well, let us find the time and then figure it out. But it does seem reasonable since we are introducing a species of frog. Now, whenever you introduce a new species, there is less competition, right? So their population could actually grow very fast. Let's first find the time. So 10,000 is equal to 617, 1.265 to the power of t. So we'll divide by 617. So 10,000 divided by 617 equals to 1.265 to the power of t. Now we can take log both sides and then solve, right? So we get log of 10,000 over 617 equals to t times log of 1.265. So t is equal to log of 10,000 divided by 617 over log of 1.265. Correct? Let's find this answer. So we have log of 10,000 divided by 617, and we'll divide this by log of 1.265, 11.849. Let's say 85. So almost 11 years and 10 months, right? So that is the time when the population will increase to. So we can say 11 years and 10 months. So that is the time required for the population to grow to 10,000. It seems to be reasonable since new species of frog introduced may not have competition, right? And we have already seen that in the 7 years it has grown. Since we have seen a growth rate between 5th to 7th year, so another 11 years, to go to make it 10,000. So total time, that means 4 more years to go to make it to 10,000. So that is quite reasonable. I hope that makes sense. Feel free to write comments and share your views, and if you like and subscribe to my videos, that'd be great. Thanks for watching and all the best.